Hello friends, welcome to the video lecture series of the subject Basic Electrical Engineering. Myself Pankaj Shah. So you have seen DC circuit in previous video. So in today's lecture, I am going to explain very important topic of this chapter, and that topic is Ohm's law and resistors connected in series and parallel. You might have heard this term Ohm's law, and also you know the equation of Ohm's law, but you never remember the statement of Ohm's law, which is the correct statement of Ohm's law. So let's see what Ohm's law suggests. So before going to the statement of Ohm's law, let's consider this figure. So in this figure we have considered one piece of conductor or one piece of wire which is having resistance R. So we have represented that conductor in terms of its resistance. So some resistance R is connected with the battery voltage. And you can see that this battery voltage, supply voltage, is the voltage V. And whenever we are giving voltage to any type of conductor, then current will start flowing through that conductor. So this I is the current flowing through this conductor. So V, I and R is the important term in Ohm's law. So what is the relationship between the voltage, current and resistance of any conductor connected in that path? So let's first see the statement of Ohm's law. So the statement of Ohm's law is the ratio of potential difference between any two ends of any conductor, or you can say the voltage applied at any conductor and the current flowing through or the passing through that conductor remains same. So basically the statement is the ratio between voltage and current remains same if physical parameter does not change and temperature remains constant. So this is the very basic statement of Ohm's law. The ratio between voltage and current remains constant if temperature is constant and physical parameter does not change. So mathematically we can say that V by I is equals to constant because V is the voltage and I is the current. So V by I is constant, and this constant is nothing but the resistance of our circuit. So R is the resistance of that conductor and it is treated as the constant. Let's define Ohm's law in another term. If R is constant in any type of circuit, then we can say that the voltage applied at any conductor is directly proportional to the current flowing through that conductor. So we can say that voltage is directly proportional to the current. So V is proportional to I. And if we remove proportionality, then V is equals to IR. This equation often we have seen in many examples and in many theories, because this is the only relation is being used in electrical branch. V is equals to IR is the basic relationship you can see here. So this is nothing but the Ohm's law. But there is some limitation of Ohm's law, and the limitation you have seen in this statement itself is the temperature of the conductor should remain constant. So now let's see some characteristics between voltage and current. So in Ohm's law, if you are defining or drawing characteristics between voltage and current, then it will be always a straight line because the ratio between voltage and current is constant. So that means if voltage increases, then current will increase linearly with respect to voltage. And the slope of this linear line is nothing but the R, that is the resistance. So the slope of this characteristics will be the resistance of your circuit. So in this way, Ohm's law can be defined, that is voltage is directly proportional to current, or you can say that the ratio between voltage to the current is always constant, and that constant is nothing but resistance of your circuit or of your conductor. Now, I have said that there is some limitation of Ohm's law. So now let's see some limitation of Ohm's law. So the first limitation of Ohm's law is the relationship between voltage and current is not applicable to the non-metallic conductors. It is only applicable to the metallic conductors. For example, if we take silicon carbide, then V is not directly proportional to I. In case of this silicon carbide, V is equals to K into I raised to M, where K and M are the constant of that particular circuit. So we can say that in non-metallic conductors, Ohm's law cannot be applied. Now let's see the second limitation of Ohm's law. So the second limitation of the Ohm's law is it is not applicable to the non-linear elements. And non-linear elements are just like the Zener diode or the voltage regulators. So in this type of semiconductor, or you can say non-linear devices, Ohm's law cannot be applicable because it does not follow the linearity between voltage and current. And the third and the most important limitation of Ohm's law is the temperature of the circuit should remain constant. If temperature is varying, then Ohm's law is not applicable. So this was all about the Ohm's law and its limitation. So now let's see the connection of resistors. How resistors are connected in series and parallel. So you can see this figure. In this figure, we have taken three resistors connected in series. And we have named that resistors as R1, R2 and R3. So three resistors are connected by end-to-end manner, and we have applied some source of electricity to this resistance, and that source is nothing but a battery, that is the voltage source V, and that is the DC voltage source. So we have applied V voltage to the combination of these three resistors. And if we apply V voltage to this combination, then some current I will start flowing through this combination. So this current I will be same in all three resistors. But the voltage, that is the total voltage applied to this combination, will not be same at three resistors. Voltage will be distributed. In series connection, voltage is always distributed. So we can say that V1 is the voltage across the first resistor, V2 is the voltage across the second resistor, and V3 is the voltage across the third resistor. And according to Ohm's law, you can define the equation of V1, V2 and V3. So now what is our aim to find in this theory is we want to replace these three resistors by an equivalent resistor. That means we do not need to put three resistors in series to get the effect. Instead, we can put only single resistor. But what will be the value of that equivalent resistor? That is the aim of our theory, to find the value of the equivalent resistor. So now let's derive the value of that equivalent resistor. So for that, first we will write the equation of the potential difference across all these three resistors. And the equation for the potential difference across all three resistors is V1, V2 and V3. And according to Ohm's law, V1 is equals to I into R1, V2 is equals to I into R2, and V3 is equals to I into R3. We have just seen the Ohm's law. So V1 is equals to IR1, V2 is equals to IR2, and V3 is equals to IR3. Now let's apply KVL to this circuit. If we apply KVL to this circuit, then we know the Kirchhoff's voltage law. The applied voltage to any circuit should be equal to the voltage drop or rise in the elements connected in that circuit. So if we have applied V voltage to this circuit, then the voltage drop across each element, addition of the voltage drop across each element should be equal to the V. So we can say that V is equals to V1 plus V2 plus V3. Now let's put the equation of V1, V2, V3 from the above equation. So if we put V is equals to IR1, V1 is equals to IR1, V2 is equals to IR2, and V3 is equals to IR3. And the equation will be like this. If we take I as constant common from this term, then I, and in bracket there will be R1 plus R2 plus R3. If we take I on this LHS, or you can say left hand side, then V by I is equals to R1 plus R2 plus R3. But look carefully this side. V by I is nothing but the applied voltage to any circuit, and I is the total current flowing through this circuit. So this means that the applied voltage to the current, this is the ratio of applied voltage to the current. And we know that the ratio of voltage to the current is always constant, and that constant is known as the resistance. And if we see this figure, then the resistance of this figure is nothing but the total resistance, that is R equivalent. So we can put R equivalent in this equation. So if we put R equivalent in this equation, then our answer is R equivalent is equals to R1 plus R2 plus R2. So in this way, we have derived one relationship between the resistor connected in series to the equivalent resistance. So means if three resistors R1, R2 and R3 is connected in series and you want to derive the equivalent resistance instead of that three resistors, then you can just add the values of that three resistor and you get the value of the equivalent resistance. So this was the resistors connected in series. So now let's see some important law, that is the voltage divider rule in the resistors connected in series. So the same figure we have taken, three resistors R1, R2 and R3 are connected in series N to N. We have applied some voltage V to this combination, and due to the voltage V, I is the current flowing through this series combination. So if I want to find the voltage drop across the first resistor, that is V1, or V2, that is the voltage drop across the second resistor, or V3, that is the voltage drop across the third element, third resistor, that is V3. But we know the equation of V1, V2, V3 is IR1, IR2, IR3. But I don't want to find the current, because I want to find the voltage drop across the first resistor directly without finding the current. So how we can find the equation of V1 directly? So for that, we have to first find the total current I. To derive this equation of voltage divider rule, first we have to find the current I theoretically. So the equation of current I is nothing but the total voltage applied to this circuit and the total resistance of this circuit. So you can see here the current I is equals to V upon R equivalent. And we can put this equation of current I into this three equations. So if we put this current I into the first equation, that is V1 is equals to IR1, and instead of I we will put V upon R equivalent into R1 because it is IR1. So V upon R equivalent into R1. So that means we have eliminated current I from this equation. So now what equation we got is V1 is equals to V total supply voltage V into R1 upon R equivalent. So this is nothing but the voltage divider rule. So similarly, if you want to find the voltage drop across the second element, then what will be the equation of V2? So V2 is equals to V, that is the total supply voltage, into R2 upon R equivalent, that is R1 plus R2 plus R3. Similarly, if you want to define the voltage divider rule for the third element, that is V3. So V3 is equals to total voltage V into R3 upon R1 plus R2 plus R3. So in this manner, you can find the voltage across any element that is connected in series without measuring the current of that circuit. Okay, so this was all about the voltage divider rule. Now let's see what is the equation of the equivalent resistance if three resistors are connected in parallel. How we can connect the resistors in parallel? So the answer is we have to connect the similar terminal of all the resistor. We have to combine that similar terminal to make a junction. So you can say that all the positive terminal should be connected together and all the negative terminal of resistors should be connected together. So in this manner you make a parallel connection. So this parallel connection you can see in this figure. This parallel connection is supplied by the same DC voltage source battery by V volt. And by applying this V volt to this combination, I is the current flowing through the circuit. But you can see in this figure, now voltage applied to each resistor will be same. Now because it is a parallel connection. But current flowing through each path will be different. So that means current flowing through first path will be I1, current flowing through second path will be I2, and current flowing through third path will be I3. But voltage across each element will be same. In series connection, voltage was different and current was same, and in parallel connection, voltage is same but current is different. Now, our aim in this theory is also same. Our aim is to just eliminate this three resistors connected in parallel, and we want to just put one single resistor instead of this three parallel combination. Means we want to find the R equivalent in this theory also. So how we can find R equivalent from these three resistors connected in parallel? So for that, first we define the current flowing through each resistor. So the current flowing through the first resistor, that is the R1, is I1, and according to Ohm's law, I1 is equals to V by R1. Similarly, I2 is the current flowing through the second resistor, and I2 is equals to V by R2. Similarly, for the third resistor, I3 is equals to V by R3. So you can see these three equations, I1, I2 and I3. Now in the past, that is the series connection of the resistor, we have used the Kirchhoff's voltage law. Here we have to use the Kirchhoff's current. And Kirchhoff's current law states that the total incoming current towards any node should be equal to the outgoing current from that node. So you can see this figure. In this figure, this total current I is incoming towards this node A. And this I1, I2 and I3 is the outgoing current from this node. So we can say that this total incoming current I should be equal to the I1 plus I2 plus I3. We have just obtained this value of I1, I2 and I3 as V upon R1 plus V upon R2 plus V upon R3. If we take V common from this equation, then in bracket it will be 1 upon R1 plus 1 upon R2 plus 1 upon R3 like this. And if we put V in the LHS side, then it will be I upon V is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. And we know that V upon I is the total voltage to the total current is always constant, and it is known as the resistance. But I upon V will be 1 upon R equivalent. So the equation of the equivalent resistance can be written as 1 upon R equivalent is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So in series connection, resistors are directly added, whereas in parallel connection, if you want to find the equivalent resistance, then there is an equation as 1 upon R equivalent is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on. The equation will depend on the number of resistors that you have connected in parallel. So in this way, you can find the equivalent resistors in case of parallel resistors. Now let's see the important rule in parallel connection, that is the current divider rule. And in current divider rule, again we have taken the same figure, but here our question is to find the current flowing through each resistor without finding the voltage. Because we know that the current flowing through this first resistor I1 and this second resistor I2 is nothing but, according to Ohm's law, I1 is equals to V by R1 and I2 is equals to V by R2. But I don't have any data of the voltage V, and I don't want to find the voltage V. I want to find the current flowing through this resistor directly. So for that, let's see this diagram. So let's first define the V. If you want to eliminate V from this first equation, then you have to find the value of V first from this V. So we know that V is equals to IR according to Ohm's law. So V is equals to I into R equivalent of this circuit. And we know that 1 upon R equivalent is equals to 1 upon R1 plus 1 upon. And if we solve this R equivalent, or you can say RP, that is the parallel resistors, then it will be product by sum. Product will be R1 R2 and summation will be R1 plus R2. So you can directly put this RP in this equation. V is equals to I. So you get V is equals to I into R1 into R2 upon R1 plus R2. Now you can put the value of V in all these three equations or in all these two equations. So if you put this value of V in the first equation, that is I1, then it will be I1 is equals to V upon R. So if you put the value of V in this equation, then it will be 1 upon R1 will be outside, and inside you have to put the value of V, and the value of V is nothing but the capital I in bracket R1 R2 upon R1 plus R2. So here there is 1 upon R1 and here there is R1 R2. So R1 R1 will be cancelled. So there will be the equation of current I1 as I1 is equals to total current I into R2 upon R1 plus R2. So in current divider rule, you can say that there will be the opposite resistor in the numerator. In voltage divider rule, the resistance at which you want to find the voltage was in numerator, whereas in the case of parallel parallel resistors, you can say that the opposite resistors should be on the numerator. Similarly, if you want to find the current flowing through the second resistor, that is I2, then the equation will be like I2 is equals to total current I into R1 upon R1 plus. So this was all about the resistors connected in series and parallel. Thanks for watching this video. Stay tuned.